Hello and welcome back to section 2.2 basic differentiation rules and rates of change. So we're going to continue on with a couple more examples. We're asked to differentiate each of the following functions, and so probably our best bet in this case is to rewrite these functions to make our lives a little bit easier. You're always looking for constant multiples, and you'll notice that 5 halves is a constant multiple. So if I rewrite this, I could write it as y equals 5 halves, and then x to the 3 on the bottom could be written as x to the negative 3. Now we can follow our power rule, and it just makes life easier. We don't have to do anything with our the 5 halves except for multiply by the power and things like that. So when I differentiate y, I get dy over dx, and that will equal 5 halves times negative 3 x, and then when I reduce negative 3 by 1, I get negative 4. So now, if I do a little simplification of this, dy dx will become negative 15 halves x over x to the fourth. And that would be my final answer, fully simplified for that one. Then for the next one, when I could rewrite this one, and it's a little bit trickier because this 2 is cubed. Well, probably what I would do, just to make my life easier, is I would cube the 2 and cube the x. Since there's no addition or subtraction, I can just cube each term. So I might write it as y equals 5 over 8x cubed. And so when there's addition, that's where you got to like FOIL things out, but when addition or subtraction, but when it's multiplication, you can just cube each term. And so now I'm back to the same type of problem I had before, where 5/8 is a constant multiple and x cubed is a power, and so I could just write it as dy, I would just write it, I'd rewrite y so that I get the x cubed off the bottom, and so I'd write it as y equals 5/8 times x to the negative 3. Now, if I go dy dx, differentiate it, I will end up with 5/8 times negative 3 x to the negative fourth. And so my final simplification for that is going to be, the differentiation is going to be dy dx will equal negative 15/8 over x to the fourth. And so that's probably what we're looking for. That's the best answer I can get, fully simplified. And I just changed the negative 4 back to a positive 4 and put it on the bottom, just like I did in the previous one. So in the next one, you can see that the 7/3 again is just a constant multiple, so I can leave that alone. And since we have x to the negative 2 on the bottom, actually I'm going to flip it up to the top, and I'm going to rewrite this as y equals 7/3 x squared. Now I just follow my power rule. Dy dx, differentiate, and that will be 7/3 times 2, and when I reduce the power by 1, 2 minus 1 is 1. I could put a 1 there, but I'm not going to. And so now it's just simplifying this to get my final answer. So dy dx will equal 14/3 times x, and that would be probably the best answer you can get for that one. And then finally, the last one, same type of thing, actually. Oh, there's supposed to be parentheses around this guy. And so what ends up happening is, if I was to take this to the negative 2, basically what that means, it's y equals 7 times 3x squared, if I get it off the bottom of the fraction, and then I can square both of these numbers since there's no addition or subtraction. So the rewriting of this would be 7 times 9x squared, which is really 63x squared. And now I can go ahead and differentiate, and so dy dx will equal 63 times 2x, and the x got reduced by 1, power got reduced by 1, and so then 63 times 2 is 126. So final answer is dy dx equals 126x. And so that's what we're looking for that one. So that's what we're doing when we're differentiating. Rewriting them could be very helpful. So in the next one, we want to find the derivative of each of these functions. And basically what happens is this, that we talk about that you can, since we've been just doing a power rule, we could do it on single single terms, now we can do it as a group and just kind of add and subtract them together. So when I go ahead and differentiate this, I could do them all separately and combine them back together, or I could just do them all at once. So I'm going to differentiate this and go through and follow my power rule. So that means it becomes 3x squared. Now this guy right here becomes, well, there was a power of 1 there, so it's negative 4 times 1. I'm not going to write the times 1. And then when I reduce the power of x by 1, it becomes x to the 0, which just gives me another 1. So it's really negative 4 times 1, which is just negative 4. And then our constant of 5, remember when we take the derivative of a constant, is 0. So the derivative that I get for these functions are 3x squared minus 4. So just like before when we were doing single terms, now we can do it with polynomials, and we can just go through step by step by step. So for g of x down here, I would start probably by rewriting it. Make things a little bit easier. I've got a negative 1/2 x to the 4th plus 3x cubed minus 2x. So now if I go ahead and differentiate this, I can go ahead and power rule, so it's negative 1/2 times 4 x cubed plus 3, now multiply by the power and then reduce the power by 1, minus 2, and when I multiply by the power, which is 1 there, it becomes times 1, but then x to the 0 is also 1, so I get a 1, so I lose my variables there. So my final answer for this one, when I get it all simplified, is negative 1/2 of 4, which is negative 2x cubed, plus 9x squared, minus 2. Now remember, these derivatives are slopes of the tangent line, so that's really what we're doing. These are slopes from the original function. So in my next example, we're going to do some trig functions, and you just have to remember our rules of trig. And so if we do y sine 2 sine of x, we just have to remember what the derivative is. Since this is a constant multiple, the 2 is just left alone. So we're going to say y prime equals 2. Now when I take the derivative of sine, I believe it becomes cosine of x, and therefore that's what I end up with for my answer. The next one, I rewrote it for you, and so y is equal to 1/2 sine of x. And you could have it sine of x over 2, the whole thing over 2, but you can write it as 1/2 sine of x. And so now when I take the differentiation of that, y prime, I leave the 1/2 alone, and sine goes to cosine again. And so then for the final one down here, I get y equals x plus cosine of x. And so now I can just go through. This is just like a polynomial, even though cosine doesn't really fit the polynomial pattern. But I can go ahead and take the y prime, I'm going to call it dy dx this time because it's the same thing, equals, now remember that the power of x was 1, so I multiply by 1, and then I reduce the x by a power of 1, which is x to the 0, which is times 1, so I'm just going to say 1, and then when I take the derivative of cosine, it becomes negative sine, and so that is my final answer for this one. So now we're going to talk about a billiard ball being dropped from the height of 100 feet in the air. And we have this function. It's 100 feet in the air and the ball's being dropped. And so remember that negative 16t squared is the acceleration due to gravity. And the key to this one that you got to pay attention to is average velocity. So whenever you see average velocity, it's different than just velocity. Okay? If they ask for instantaneous velocity or they ask you for just the velocity, they're asking for derivative. Average velocity, they're asking you for slope. And they're giving you 2 points to find the slope between them. And so we have to do change in y over change in x. So we'd say s of t. We would do s of t minus, we do our whole limit process. But we're just going to go ahead and just do change in y over change in x. So we do change in y over change in x, and that's our slope. And so if first of all I need to find out what s of, so it's going to be s of 2 minus s of 1 all over 2 minus 1. That's my change in y over change in x. So I need to find out what these s of 2 and s of 1 is. So I previously graphed the function just so I could do this a little quicker. And so if I do s of 2, I'm going to go second and find the value at 2. Plugging that in, I get 36, and then s of 1 will be, s of 1 is 84. So now I can say it's really my slope will be 36 minus 84 over 2 minus 1. And with a little bit of simplification on this, I end up with negative 48 over 1, which means my average velocity between 2 and 1 seconds is negative 48 feet per second squared. Which I don't have room to write it, but it's feet per second. So feet per second. So then, if I want to find the average velocity between these 2 points, 1 and 1.5, again, we're doing slope. So this time it's s of 1.5 minus s of 1 over 1.5 minus 1. So I already know what s of 1 is. It's 84. But I need to find out what s of 1.5 is, so I'm going to use my graph again. And this time I'm going to do value at 1.5. And it tells me it's 64. So 1.5 is 64 minus 84. 64 minus 84 over 1.5 minus 1, which basically will give me, looks like 20, negative 20 over 0.5, which means we have a negative 40 feet per second squared. So you can kind of see that this is kind of a limit process, and we're trying to get closer and closer so that we can find out what 1 is, what the instantaneous velocity at 1 is. So this time I'm going to find the average velocity by using the slope again, but this time I'm going to use 1.1 and 1. And so if I simplify this, I got to find out what the value is at 1.1. Oops. At 1.1. And that is 80.64. So I've got 80.64 minus 84 all over 0.1, which then will simplify when I subtract those to a negative 3.36 over 0.1, which means it's negative 33.6 feet per second. So as we're getting closer and closer to 1, and both of these guys being 1, we're getting closer and closer to the instantaneous velocity. And so what ends up happening here is that you can see if we got a little closer, we might get closer and find an exact value. What you'll notice, though, is since the object is falling, that the velocity is negative, and anytime an object falls, the velocity is negative. So then my last example is about a diver diving into the water, and we have a couple questions we need to answer. And so we have this platform that's 32 feet in the air, and he's adding an initial velocity of 16 feet per second. That's what this is, and then the acceleration due to gravity. So the first question is, when does the diver hit the water? Well, if you think about it, you've got a diver jumping off a platform up here, and the water's down here. So the diver is going to jump off, and he's going to fit the pattern of a parabola. So it's going to look something like this when he splashes down in the water. And so we need to figure out when he's on the ground. Well, if he's 32 feet in the air to start with, and he hits the water down here, well, what is his height? Well, his height is 0 because that's where he started at. So we're going to take, for A, we're going to take negative 16t squared plus 16t plus 32 equal to 0, because that's when he hits the water. So if we can find out what t is when he hits the water, then that's going to be very helpful to find our velocity at impact. So we have to simplify this. I'm going to factor out a negative 16, make my life a little bit easier, and so I get t squared minus t minus 2 equals 0. And so by just doing a little bit more algebra here, I can factor and get t minus 2 and t plus 1 equals 0, which means that my time that it takes the diver to hit the water is either t minus 2 equals 0 or t plus 1 equals 0. And so t equals 2 seconds or t equals negative 1. Well, since we can't go back in time, we're not going to use the negative 1. So 2 seconds after he jumps off the diving board, he hits the water. So now that I know how long it takes for the diver that's up here to hit the water, I can find out the velocity at impact, because if we know the derivative of this graph, we can take the slope of the graph, that's the velocity when it'll hit the water, and we know how long it takes, that's t. We can do that. That's what we're finding. So I'm going to go ahead and say, okay, well, we have s of t, which was my original function, is negative 16t squared plus 16t plus 32. If I take the derivative of this, following all my power rules, negative 2 times negative 16 is negative 32t, and then plus t to the first times the 16 gives me just plus 16. The 32 will drop out because it's a straight line. So now this is the slope of the tangent line at any given point, which is also the velocity at any given point, and the point that I want is 2. So I want to find out what's the derivative at 2, and so now it's just a matter of me plugging in 2 in for t and simplifying, and I get negative 64 plus 16, which I believe the diver hits the water at 48 feet, negative 48 feet per second, which is really what we're trying to find. And it's just a coincidence that we got the same number as one of the last ones. So thank you for listening, and I'll talk to you guys soon.